Class 11 Chemistry, Structure of Atom.
Ever wonder why we study the atom? They are the building blocks of everything. Structure defines their chemical properties. This creates amazing modern technology. Let's learn it more.
Hello, class. Welcome to the story of chemistry, the story of the atom. Over the next few minutes, we'll travel from the very first discovery of tiny particles all the way to the electron cloud. It's an amazing journey of how scientists figured out what makes up everything around us. Let's begin. Our story begins with the discovery of 3 tiny particles. First, J.J. Thomson discovered the electron, a negative particle. Then, Goldstein found the positive proton. And finally, James Chadwick discovered the neutron, which carries no charge at all. Together, these 3 particles build every single atom in the universe. Next, let's meet the atomic number and mass number. The atomic number Z is the number of protons. It decides which element you have. The mass number A is protons plus neutrons. 2 atoms with the same number of protons but different neutrons are called isotopes. And atoms with the same mass number but different protons are called isobars. Isotopes, same element, different weight. Isobars, different elements with the same total weight. Our first model comes from J.J. Thomson. He imagined the atom as a positive pudding with electrons embedded inside, like raisins in a pudding. That's why it's called the plum pudding model. But it had a problem. It couldn't explain why the atom stays stable or why elements emit only certain colors of light. So the story. Then came the famous Rutherford experiment. He fired tiny alpha particles at a thin gold foil. Most shot straight through, proving the atom is mostly empty space, but a very few bounced back. That meant there's a tiny, dense, positive nucleus right at the center. This gave us the nuclear model of the atom, but it still couldn't explain why electrons don't spiral into the nucleus. Niels Bohr then suggested that electrons move in fixed, stable orbits around the nucleus. Energy is only absorbed or released when an electron jumps between orbits. This model beautifully explained the hydrogen spectrum. But it only works for hydrogen-like atoms with a single electron. The story wasn't finished yet. Let's talk about shells and subshells. Electrons live in main energy levels called shells, K, L, M, N. The maximum electrons in a shell is given by 2n squared. Each shell splits into subshells called S, P, D, and F, which hold 2, 6, 10, and 14 electrons respectively. Here's one of the most amazing ideas in quantum physics. Light behaves as both a wave and a particle. The physicist de Broglie realized that matter must also have a wave nature. The relationship is wavelength lambda equals h divided by mv. For a big object like a cricket ball, the wavelength is tiny and invisible. But for a tiny electron, it becomes noticeable. Wave-particle duality. Then comes the surprising Heisenberg uncertainty principle. It tells us we cannot know both the exact position and exact momentum of a tiny particle at the same time. The product of their uncertainties is always greater than or equal to h over 4 pi. For big objects, we don't notice it, but for electrons, it's very important. Instead of fixed orbits, we now talk about orbitals, regions where electrons are most likely to be found. To describe each electron completely, we use 4 quantum numbers: n, the principal quantum number for the shell; L, the azimuthal for the subshell; m, the magnetic for orientation; and s, the spin. Together, they give the full address of every electron. These orbitals have beautiful shapes. An s orbital is a simple sphere. A p orbital looks like a dumbbell, pointing along the x, y, or z axis. And the d orbital looks like a four-leaf clover. So spheres, dumbbells, and clovers. That's the family of atomic orbitals. To build an atom's configuration, we follow three friendly rules. Aufbau's principle says, fill the lowest energy orbitals first. Pauli's exclusion principle says, each orbital can hold a maximum of 2 electrons with opposite spins. And Hund's rule says, fill each orbital singly before pairing them up. Together, these give us the electron configuration. Let's write some configurations. Oxygen has 8 electrons, 1s2, 2s2, 2p4. Iron has 26. Now, a special bonus. Half-filled and completely filled orbitals are extra stable. So chromium becomes 4s1, 3d5, and copper becomes 4s1, 3d10. One electron jumps up to make the d subshell half-filled or full. That's why they're special. And that completes our story of the atom. We discovered the particles, traveled through the models of Thomson, Rutherford, and Bohr, met the shells and orbitals, and learned the 3 rules of filling electrons. Remember, understanding the atom unlocks all of chemistry. Wonderful work today, class. See you next time.
Video by Anand Mohandas.